that's just a look at some kind of the national data, some early data, and then we started doing more research here. We initially developed bioretention media specifications, 60% sand, 40% compost years ago, 2009. The paper for developing that is sitting outside. It was a project through Puget Sound Partnership, and WSU, myself, led that, and it was a few $1,000s to develop a media that was permeable, grew plants, and was kind of local materials and all that. And so we were successful at that. we developed a media that was permeable. It actually grows plants like crazy, championship plants, and it actually treats some contaminants very well. Then the WSU research facility came online. We started monitoring doing research on the water quality of the water coming out of bioretention. And at the same time, Herrera, through City of Redmond, started monitoring bioretention swales out in the field with this compost mix. And then the red flags went up. This is a graph from that City of Redmond study. Total phosphorus, milligrams per liter on the vertical axis, time on the horizontal. That's basically February, March through August. It's about a year and about a year and a half. The blue line is the water going in, total phosphorus. Water's pretty clean going in. Red is coming out. Bad picture. Those are high numbers. And at the same time, those horizontal lines, potting soil extraction. Okay, so this is the SPLP extractions, weak acid extractions. Testing the soil that the plants are coming in. Oh, is it the plant soil that's getting stuck in the ground? Compost extraction, mulch extraction, and then the sand extraction. So now you're testing each of these to try to figure out where is this stuff coming from, and then you can see an industrial benchmark there. For total phosphorus, this is somewhat a normal flushing pattern. We're actually seeing more commonly, actually the flushing go up. So you'll start testing, you put the stuff in the ground, you start running water through it, you start at some level, and actually then it increases, the concentrations actually increase, and then they start to come down. So that's actually the more typical flushing pattern that we've been seeing from bioretention media. But the message here is, we've got an initial flush here, and and then it goes down, but still remains quite high. I mean, for the most part, up above 1 milligram per liter. We should do better than that. Copper, dissolved copper, and same kind of story. Although you see the influent fluctuating a bit there. But starting quite high. We've seen higher than this, actually significantly higher. 50 micrograms per liter is not uncommon to start. Also, not a good picture. And the same extractions. Now, do you see the line there, acute water quality criteria? That is where there is a lot of work going on around that whole issue right now. And we have to do better with copper. There is a question on how toxic copper actually is coming out of bioretention areas. And in fact, the most recent research is showing that the water coming out of bioretention areas with even this level of copper, that initial level, 20, 25, that copper is not bioavailable. It's bound up, and we think it's primarily bound up in dissolved organic carbon. I don't know, have any of you seen effluent from bioretention areas and it looks like tea? Looks like compost tea. A lot of that compost tea is dissolved organic carbon, fulvic and humic acids. And the copper's likely, we think, pretty sure it's bound up to that and not bioavailable. So, nevertheless, there's water quality treatment criteria we need to meet. But the good news is it appears that copper is bound up quite tightly in the effluent from bioretention areas. So that's good. That's the good news. We saw virtually, and the first two papers on this research is now out, so you can get that. I should have brought that actually. Those papers are out, and we in those papers it's very positive results in that virtually eliminating all sublethal effects to fish, and Daphne, another target organism. With the effluent from bioretention areas. So that's really, really good news. More work to do there. Any rate, so the red flags go up. Uh-oh, we got a problem. We're exporting, more is coming out than is going in. That's not a good picture. Now, I want to show you some research from the WSU LID research facility, and you see all those white tanks on the right? This is data from those white tanks. So there are different soil media treatments in those tanks, replicated 4 times. So there's some with less compost, 80% sand, 20% compost. Some with other stuff in it, 60% sand, 15% shredded bark, 15% compost, 10% WTRs. Anybody know what WTRs are? Residuals. Iron and aluminum hydroxides out of drinking water plants. And so iron and aluminum are very good, hydroxides are very good at binding phosphorus. So we put some of that in there to see if can we bind up the phosphorus. So anyway, a bunch of different treatments, and you see the analyte total suspended solids, dissolved zinc, copper, phosphate, PO4, nitrate, NO3, and then bacteria. And these are some results. This does not include the first flushing. We didn't have the money to do the first year, so there's a whole year of water that went through this stuff before we were able to start sampling. But after about 2 years, this is what we were seeing coming out of those systems. And the important columns to look at are the median influent. Do you see that? Median influent. So that's median is just a measure of central tendency for this data. And you can see N is the number of measurements, 36. We have 36 measurements for TSS through those tanks. And then the other important column is median effluent. You know, the rest of it is interesting, but those are the 2 important ones. So you see some pretty good numbers here. 4.9 for TSS going in, that is super low. That's very clean water. 5.3 coming out, that's really good. Dissolved zinc, 71 going in, that's a pretty typical number at or below detect, 4 micrograms per liter. Great performance on zinc. Dissolved copper, okay. 3 going in, that's super low. And you might expect that you'd get more coming out because that's such a low number. It'd be very easy to find a little bit more copper in almost anything, certainly sand or certainly compost. 8.6 coming out. That's still okay, that's a pretty good number. The phosphate is the bad boy here, over a order of magnitude coming out than going in. And this is something we've seen consistently and remains, again, our biggest challenge. Nitrate, okay, not bad. Anything between 30 to 50% reduction is very typical for nitrate out there in the world. The new media we're working with, we're getting some really good nitrogen numbers. Also some good phosphorus numbers. And then bacteria, excellent. So these are colony-forming units per 100 milliliters water. 22.5 coming out with 229 going in. That's very good. So that 22.5, that's solidly in human contact level. That's very, very good number. There's more sampling coming from this research. We've just finished a whole nother set of data on the high-performance media. We're in the middle right now of writing a synthesis paper for the state, actually through Redmond, but the state money, to kind of bring as many studies as we can together and sort of start drawing some conclusions for the studies we've done so far, and then spell out kind of the next steps. What do we need to do next? Which we kind of already know what we need to do, and it's just a matter of getting the money together and getting to it. But what we're hoping is within the next year to 2 years is to have a specification, and there'll probably be more than one. We'll probably still have the 60-40 for some applications, no underdrain, good subgrade soils, might work fine. Other specifications for other settings where you have underdrains, receiving waters, depending on that receiving water. What we're hoping for is in the next year to 2 years is to have a solid specification for the high performance stuff. You have an underdrain, sensitive receiving water, media for that. All right. So just there's generally been the thinking that, oh, all this stuff comes from the compost. Not necessarily so. The compost seems to have most of this stuff in it. You know, is it any surprise? I mean, we put compost in our gardens to grow plants. So any surprise there's nutrients in them? Well, there shouldn't be. So that's the primary source, but there are also going to be other materials. Sand. So here's some numbers from sand that we measured from those extractions. Wow, 14 micrograms per liter of copper, or that's actually, sorry, milligrams per kilogram. This is soil. But the surprising number to me there was the nitrate. Nitrogen in the sand? Who would have thunk it? So, not just the compost. Last bit of slides on treatment, and these are to just kind of illustrate some points. Okay, so this is some of the same data looking from those white tanks at WSU, and but looking at it graphically, box plots. Okay, so what are these box plots? Look at those ones down lower. Box plot is a great way of looking at data. What it tells you, that dark line, that's median concentration. So you have 25 measurements. What's kind of the central tendency of that measure, of those 25 measurements? That's the dark line. 25th percentile, lower end of the box. Upper end of the box is 75th percentile, and then your high and low measurement are the whiskers. Okay, so that's what those box plots tell you. So influent on the far left for dissolved copper. And then you see on the right the different treatments. So there's 4 replications of 60-40. There's the 60-40, right? Our current specification. 80-20, 80% sand, 20% compost, and so different treatments. Pretty good numbers for dissolved copper. That's about as low as you could ever expect. That's pretty darn good. Again, this is 2 years into water running through these things. TSS, the message here that's really interesting is that on the left is a plot showing the influent, which is quite low. So this is concentrations, low concentrations going in, and about the same coming out. Just under 5 coming in, and somewhere around 5 going out. So that's pretty good. Then we put a bunch of sediment in the water and ran it through the bioretention areas, over 100 milligrams per liter, and we get about the same coming out. It was around 5 coming out. So the message here from this research was that, wow, it doesn't really necessarily matter how much we're putting in. We're getting the same low number coming out. That is kind of unusual for a stormwater treatment facility. Often it's quite influent dependent on what comes out. Bioretention, it seems to be, well, you can shove a bunch in there or very little and you get very little coming out. So that's good news there. So what do we think we know on water quality treatment? In fact, we're darn sure. From the 60-40, from compost-based bioretention media, there is an initial flushing of nitrogen, phosphorus, and copper at low concentrations, and often typical stormwater concentrations. We think the nitrogen and phosphorus the flushing comes down fairly low after a year, or maybe up to 2. We don't know where the phosphorus ends. We haven't done that many years. Although the WSU facility will have, soon we'll have some more phosphorus information that will be 3+ years out. So that'll be helpful. But phosphorus, so far in a lot of the work we're doing, looking at 1 and 2 years, it just keeps going. It's still flushing too high concentration of phosphorus. Excellent zinc capture at installation and very good copper capture at typical influent concentrations after an initial flushing. The initial flushing is a problem, but copper seems to go down to fairly reasonable levels after a while. Zinc is good right out of the gate, works well. Reasonable total nitrogen capture. We've also completed some research where you can use an elevated underdrain, and we'll talk about the design of elevated underdrains for denitrification. We cover that tomorrow, not today. If you're concerned about nitrate, if you're concerned about nitrogen, there are ways to physically configure your bioretention area to reduce nitrate. And we'll look at, and that's through an elevated underdrain. And we'll show you how to design for that. Phosphorus is the bad boy. We are still working on that. And overall, we've seen some good performance compared to other technologies, except for these 3, except for the phosphorus, nitrogen, and copper.